As promised, I wanted to do a quick summary of types of sums of squares because many of you have asked about it. And in order to do that summary, I'm going to borrow from notes that I've presented in the past for my graduate stats class. That is just basic regression or basic ANOVA. And the best way to explain this is via Venn diagrams, and then I'll show you what the conditional statements are in terms of sums of squares. So what this is a summary of the sums of squares that are estimated, and I'm mostly going to focus on the Venn diagrams and available on the same course website as this video is linked to. You'll be able to see the printed or PDF form of this. So to begin, I want to show you a Venn diagram that's a little bit more complicated than what I've shown you in the past. I have an A, which is a primary predictor, and B, which is a secondary predictor maybe, and then a Y, which is my criterion or outcome. And now I have an AB, which is the interaction that is A and B together. And I notice that I shifted it up, and the reason why I shifted it up is just for clarity and ease of demonstration and all of that. It also is shifted up a little bit to make a point that may be spurious and may also be something that's just more a matter of convenience. So I'm going to zoom out here and I'm going to show you that I start out with this Venn diagram, and this is a two predictor linear model with a moderation as well. So the first type of sums of squares, and remember I told you in class that this is a SAS-ism, and the SAS Institute and the folks there have come up with these different types of sums of squares. They don't really exist in the world. They just exist in nomenclature, mostly in SAS and in SPSS, and some other stats packages use this, but not all do. So to be clear, you may have a stats package that doesn't really explicitly state these things. So type 1 sums of squares is hierarchical partitioning or ordered or sequential partitioning of the sums of squares. And what I want to emphasize is really, again, the Venn diagrams. You can go through all the text again on the website. So when I'm testing hierarchically, what I'm doing is I'm attributing all of the variance hierarchically to the effects. So what I would do is I would say in type 1 sums of squares, if the primary predictor is A, secondary is B, and then I test my interaction, in type 1 sums of squares, this A portion and the C portion all get attributed to A, and this is the common variance, and this would be like the coefficient of determination between A and Y. And then B gets this leftover portion, and this little B section is the common variance between B and Y taking A out. Okay, and then finally, the interaction gets the residual variance after both main effects are taken out. So you notice that there is a hierarchy within the main effects. A gets priority over B, and then B and A get priority over the interaction. That's type 1 sums of squares. Type 2, so again, this is a hierarchical test. Type 2 is a non-ordered hierarchical test. So what that means is that any effect that's of the same level does not get preference over any other effect at the same level. And you'll see this is pretty obvious here. A and B are both main effects, so they don't get preference over one another. And what happens is any shared variance gets cast away. So there's just unique variance that's attributable to A and unique variance that's attributable to B, and then the residual is attributable to the interaction. Now you notice that C does not get the variance or the interaction does not get the C part that is not attributable to A and B, because we are partialing out the variance that's attributable to both A and B before AB, the interaction, takes place. And so this is oftentimes referred to as type 2, or that it's non-ordered but still hierarchical. Okay, so within the hierarchy, within the main effects, there is no preferential treatment, but between the main effects and the interaction, there is preferential treatment. And again, you can see that this is the partitioning for the sums of squares. The third type is called simultaneous, and this is what I've found to be the best way to show this, is that any shared variance among our predictors is eliminated. And the reason why it's eliminated is that all of the effects are estimated simultaneously. And so with simultaneous effects, what you're going to see is that A and B and AB are all entered together and estimated simultaneously. So you can see this teeny tiny little piece here and this teeny tiny little piece here. Well, this is the effect of A, and this is the effect of B, and this is the interaction here. So obviously, when you partition the sums of squares simultaneously, in many respects you probably throw away a lot of variance that's attributable to the main effects, and that's not a good thing because that turns out to be residual. It's not variance that's attributable to any of the effects, and so therefore it is residual in the y. And that is a very quick summary of the types of sums of squares, and I highly recommend that anybody interested in this read my notes that are linked to the website so that you can see exactly how the sums of squares are partitioned. Now, there's a note about this that's very important, that sums of squares are oftentimes the focal part of analysis of variance. To a lesser degree, they are relevant to regression, but we'll get to how the sums of squares are relevant to regression, particularly when we kind of shift over and bridge over to the general linear model, when we are testing nominal level or categorical variables, when we're doing coding, contrast coding. And you'll see how we can replicate sums of squares and partitioned variance according to these rules in different ways within different stats packages. So use this as a general guideline. Review the notes that I have for it so that you have a deeper understanding, and then as we go along I'll refer to these different partitioning types when they're relevant.